In this video, we're going to continue looking at the graphs of transformed sine and cosine functions. This one happens to be a sine function. And what we will do is we'll talk about how the values within the function affect the shape of the graph, translations and dilations and reflections and all that sort of stuff. And then we will apply it to the parent function of the sine function, just choosing a couple of critical points to get us our basic shape. And then we will make our graph. So taking a look at the function y equals 3 times sine of 2x plus pi over 2, one of the first things we could look at is what is the period of the function. And the period of a sine function is defined as 2 pi over the absolute value of b. In this case, we will have a value of 2 for our b, and it's going to be this 2 right here if we are building off y equals a sine of bx plus c plus d. Depending on who you are and how this was officially described to you initially, this is one format for us. So in this case, our period 2 pi divided by 2 gives us a period of pi. So this would give us a horizontal shrink. So the graph, which used to have a repeatable pattern of a length of 2 pi, is going to get shrunk down to only be pi long. Maybe what we should do here is quickly draw a quick graph of the parent function for the sine function, which is roughly this, where we go from 0 to 2 pi with a minimum of -1 and a maximum of +1. And so what this tells us is that the length of this graph, which was 2 pi units long, is now going to get crunched down, and it will fit into a length that is only pi units long. So if this would be pi units, we would have the graph shrunk by half, and it would fit in that segment right there. The amplitude of the graph is defined as the absolute value of a, for our case, absolute value of 3, which is 3. That is going to be a vertical stretch. Remember that this amplitude is half of the height of the wave. And how that would affect the parent function, I'm going to get rid of the piece that we already talked about for the period. If we talk amplitude, we will be affecting the minimums, the depth, how low the graph goes, and how high the graph goes. And instead of going from -1 to +1, this 3 right here would make our maximum from 1 to 3 and our minimum from -1 to -3. The axis of the wave is going to be a vertical shift up or down. And in this case, that would be our value of d. But since there is none, the axis of the wave is going to stay as the x-axis. There's not going to be any change there. Phase shift, our horizontal translation, left or right. Our phase shift is going to be defined as -c over b. Nope, that's a b. Oh man, having trouble with my d's and b's here. A b. So this would be -pi over 2 divided by 2. I'm probably going to need to rewrite that as -pi over 2 times a half. Dividing by 2 is the same as multiplying by a half. And that gives me a phase shift of -1/4. What that tells me is the graph where the first period initially starts at 0 on the origin there, on the y-axis. I'm going to shift it to the left pi over 4 units. Oops, I'm going to have a little trouble with that. Let's put that back together. I'm going to shift that to the left pi over 4 units. So I'm going to have to be careful for that. Is there anything else to deal with? I'm looking for reflections mostly in this particular case, and I don't see any negatives, so I'm not going to have any values to work with there. Now remember, when you're dealing with your sine and cosine graphs, we kind of choose 5 critical points. The 3 zeros for the first period, as well as the maximum and the minimum. And one way to think about those critical points is that you want to draw a point every quarter of a period that from our starting point to the maximum is a quarter of the length of the whole period. That from the starting point to the next 0 is halfway down between 0 and 2 pi. The minimum is going to, let me see if I can shake those apart. I guess not. Oh, there we go. That this minimum is 3/4 of the way down, and the next 0 is all the way down. So I'm thinking about splitting this into quarters. That's going to be important as I get to my graph, and I want to start thinking about how I'm going to scale this. The fact that I have a period of 1 pi and a phase shift of 1/4 pi, that tells me that when I make my graph and I set up my axes, I'm going to probably want to scale it in such a way that works. And I'm also going to want to set up my y-axis. With my y-axis, I know I need to go from -3 to +3 based on the mins and the maxes and the vertical translation, the vertical dilation, the amplitude change. So I might go 1, 2, 3, -1, -2, -3. Thinking about the x-axis and the phase shifts, I'm going to want to go at least pi over here, but I want to be able to find the quarters in there. So I might say that this is pi over 4, pi over 2, 3 pi over 4, pi. And I'll give you that. Negative pi over this, negative pi over 2 here, -3/4, and negative pi right there. So if you need to pause the video, if you're actually writing this down and taking some notes, write it down. Pause the video, write it down, get yourself set up. All right, so we're going to be working off of that parent function graph, and I'm going to recreate it one more time here so that I don't have to flip the screen. And if I think about my graph and the critical points that I might have, the first 0, the maximum, the second 0, the minimum, and then my third 0. What is going to happen is if I start with my first 0 at 0, 0, and I think about the transformations I need to apply, I need to shift it 1/4 pi units to the left. So it's 1/4 pi. And then I need to vertically stretch it by a factor of 3, but this has a y coordinate of 0, and 0 times 3 is still 0. So I'd have that. Next, I would think about this maximum, which typically has coordinates of pi over 2, 1. Well, what I need to do is I need to shrink everything down. So actually, maybe what I'll do is I'll start with the end here. I'm going to go all the way to this end and say to myself, well, from my starting point to my ending point needs to be pi units. From here, if I make a second point, I'm going to make a second point there, and I say I'm going to start, that's 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi. So the length between now my two blue points, I'm going to fit 1 period of the sine function in there. Looking at my parent function graph, I know I've got a 0 halfway between the other two zeros. So I simply look at the 2 points I have on my graph, and I make a 0 halfway between them. Looking at my parent function, between the first two zeros, halfway between the first two zeros, I've got a maximum. So I look at my 2 zeros that I have. I know halfway between them I'll have a maximum. But that maximum is going to be at 3 because of the amplitude change instead of 1. Halfway between the second 0 and the third 0, between the middle of my period and the end of my period, I have a minimum. Here is middle of my period. Here's the end of my period. Halfway between them, I will have a minimum. And so now I've graphed so far 1 period of my transformed sine function. And then what I can do is just use the pattern to fill in remaining points to show the extended shape of my graph. Now this graph would continue forever in both directions, being a periodic function with a domain of all real numbers. But this is just what I happen to have, so I'll graph that. And that is the graph of y equals 3 sine 2x plus pi over 2 on the interval. And I graphed it on the interval from -pi to, and it looks like I graphed it to 5 pi over 4, 5 pi over 4 there. That would be this point right here. And so just another example of how to graph transform sine functions.